repeat that. It is going to be the study of chemical reactions that either utilize or generate electrical current in their reaction. Okay? So electrons are going to be very important with respect to electrochemistry. We're going to be utilizing electrical current, or we're going to be generating it via the process of chemical reactions. Okay? Okay, so this should seem somewhat familiar. Have we talked about reactions that utilize electrons as components in their overall reaction? Right, so we have, right? We've talked about various reactions that utilize the transfer of electrons in their overall chemical reaction. These are oxidation-reduction reactions, okay? So in oxidation-reduction reactions, which I will refer to as redox reactions for short, we always have a transfer of electrons between chemical reactants, right? So something is going to gain an electron and something is going to lose an electron, okay? What is the process of losing electrons called? If you lose an electron, what has happened to you? You have become oxidized, right? So oxidation deals with the loss of electrons, okay? What about if you gain an electron? What do we call that? Reduction, right? So reduction is the gain of electrons. So as a nice little mnemonic device, Leo the lion says grr, loss of electrons is oxidation, gain of electrons is reduction. It's a nice little reminder. Okay, so loss of electrons, gain of electrons, great. How do we know in a chemical reaction whether or not something has lost or gained an electron? How do we go about determining that in 151? So we assign something called oxidation states, right? So oxidation states are a nice little bookkeeping method that allowed us to keep track of electrons in a chemical reaction, okay? So for example, if I have a nice little reaction down here, on my reactants, I have calcium. Calcium has an oxidation state of 0, and I have water. In water, we have two different atoms. Hydrogen has an oxidation state of 1. Oxygen has an oxidation state of -1. As we go to the products, we find that calcium has changed its oxidation state. It is now a +2. Oxygen is a -1. Hydrogen is a +2. And then other hydrogens over here are a 0. Okay? So we're going to talk about how to assign these. I'm not just going to blow through them like this. But just looking at this, looking at these changes in oxidation states, calcium goes from a 0 oxidation state to a +2 oxidation state. So to go from a 0 to a +2, what must happen to you? Because when you're +2, you have 2 more protons than electrons. So if normally you're 0 and you're neutral, and now you have way too many protons, you're not going to gain protons, by the way. What's had to have happened? You had to have lost electrons, okay? So going from a 0 to a +2 indicates that we have lost electrons, and most importantly, we have lost 2 electrons, right? So 2 electrons is important. So loss of electrons, that is oxidation. It also results in the increase in the oxidation state. We go from a 0 to a +2, okay? On the other hand, if we look at hydrogen, hydrogen is a minus or a +1 over here. When it goes to the products, we are at a 0, right? So if it goes from a plus to a 0, what must it have gained? Had to have gained an electron, right? So if we gain an electron here, we are reduced, so we have gained 1 electron. And another telltale sign that you've gained an electron is that you have a decrease in your oxidation state and moving from reactants to products, okay? Okay, so loss of electron, oxidation, gain of electron, reduction. Really quickly, with respect to vocabulary, if I have been oxidized, right, I have lost my electrons. Who have I given them to? The other thing, what's happened to the other thing? If I've given it electrons, has it been oxidized or has it been reduced? It's been reduced, right? And so if I am oxidized, I'm giving my electrons to something else. I am the agent of reduction, okay? So anything that is oxidized, we also call a reducing agent, because anything that is oxidized has lost electrons. By losing electrons, it's giving it to someone else, so it is reducing something else, okay? So oxidation, or things that get oxidized, are reducing agents. On the other hand, things that get reduced, and the exact same idea, these guys are oxidizing agents. If you've been reduced, it's because you took somebody's electrons from them and you essentially were the agent of oxidation. Okay, so that's just a little refresher. Now, really briefly, how do we assign oxidation states? So there were a couple of rules that I'm going to quickly go over. First rule in assigning oxidation states is that if you're something in the elemental form, your oxidation state is 0. Okay? So elemental form of that thing has an oxidation state of 0. Second thing, if you are a monoatomic ion, meaning if you are a single ion, you have a charge to it, your oxidation state is just the overall charge of the ion. Okay? So for example, in number 1 here, we have chlorine. What is the oxidation state of diatomic chlorine? If I tell you that specifically, this is chlorine in the gaseous form. So this should be 0, right? Why is this 0? Because this is the elemental form of chlorine, okay? Number 2, I've got sodium plus 1 ion. What is the oxidation state of sodium plus 1? Plus 1, okay? So monoatomic ion is going to have the same exact oxidation state as it has charge. The only issue really comes in with respect to compounds, okay? So we have 3 compounds here. First one is KF. In a compound, each atom is going to have its own oxidation state, okay? One of the big rules that we have to remember, though, is that the sum of all of the oxidation states of the atoms in the compound have to sum overall to the overall charge of the compound, okay? So for example, KF, what is the overall charge of this compound? It's 0, right? So what this tells us is that the oxidation state of potassium plus the oxidation state of fluorine, they have to sum to this overall charge of 0, because that is the charge of the compound. All right, so now if we're going to assign oxidation states to potassium, and fluorine, who's most predictable? Who can we assign first? So it follows in order. Number 1, group 1 and 2 metal ions, right? So group 1 metal ions, what charge do they normally form? First column in the periodic table, +1. What about group 2? What charge do they usually form? +2. Those are the most predictable, group 1 and group 2. Does potassium lie in that? Oh, yep, there it is. Okay, so potassium is the most predictable in that, okay? So if we're going to assign these, we have a +1 plus the oxidation state of fluorine, right? We assign the most predictable things first, and then we assign the least predictable things last. So what does the oxidation state of fluorine have to be if our +1 plus whatever x is has to equal 0? -1, right? So for this guy, for K, we've got a +1, and for F, we have a -1, okay? Super easy. Now, same exact thing with something like CO2. Again, we have a compound, right? So the oxidation states of everything have to sum to 0. Between carbon and oxygen, who's most predictable? Oxygen, right? So when we talk about nonmetals, it tends to move in the order of fluorine to H plus to O2 minus, and then we don't really care about anything after that, okay? So oxygen is more predictable than carbon. What is the oxidation state of oxygen normally? -2, right? It's whatever charge it takes in the form of the ion. In CO2, how many oxygens are there? There are 2, right? So you have to account for the fact that there are multiple oxygens. So carbon is going to take on whatever oxidation state that satisfies this equation, right? So if we have 2 oxygens and they're each a -2, then what does carbon have to be with respect to oxidation state? +4, okay? So carbon here is going to be a +4, oxygen is a -2. And then finally, we have something that is charged. So SO4 2-, this is the sulfate ion. Again, we have to sum to the overall charge of the molecule. What is the overall charge of SO4? 2 minus. 2 minus, right? So for these guys, for our polyatomic ions, we have to sum to the overall charge. We're going to sum to 0. So now between sulfur and oxygen, who's most predictable? Oxygen. And again, what is its oxidation state? -2. So then sulfur has to take on whatever oxidation state to satisfy this overall equation, right? So what is that with respect to sulfur? We have to have a +6 here. So sulfur in this guy is a +6. Oxygen is a -2. Okay, so now that's just a brief refresher of assigning oxidation states. So how are we going to utilize these to determine if a redox reaction has occurred, right? So if I give you a reaction like this and I say, what's been oxidized, what's been reduced, how would you know that? You would go through, unfortunately, and you would assign oxidation states to everything, okay? So if we do that, we just go ahead and start doing it. Oxidation state of SN, 10 solid, what is this? This is the elemental form of tin, right? So elemental form of tin has an oxidation state of 0, okay? We move on to the next little molecule. We've got HNO3, right? Overall, they have to sum to 0. Between hydrogen, nitrogen, and oxygen, who's the most predictable? So oxygen is the most predictable. There is one of them, so that's a +1. Between the last two, nitrogen and oxygen, who's most predictable? Oxygen, right? So oxygen is most predictable between those two. So nitrogen is going to take on whatever oxidation state it needs to satisfy this equation. So we have 3 times -2 plus this unknown nitrogen plus a +1. So X ends up being a +5 overall. Is that right? 6? Yes, +5. So +5, -2, +1. As we move over here, we're going to have oxygen in a -2 oxidation state, right? Again, it's more predictable. If we have 2 oxygen, what does 10 have to be then? So 2 times -2 gives us a -4. So 10 has to be a +4 to balance that. Same thing with respect to nitrogen and oxygen. We have a -2 with respect to nitrogen, or oxygen. This is where it ends. Nitrogen has to be +4 because of that. And then finally, hydrogen and oxygen, we have a +1. There's 2 of them, so oxygen has to be a -2, okay? So now, in looking at all of these oxidation states, who has been oxidized? Who has gone from a reactant and lost electrons, and you would note that by the oxidation state of its product. Oxidized is loss of electrons. That usually is indicated by an increase in oxidation state. So as we go from 10 to 10 with a +4, so we go from 0 to +4. The only way to go from 0 to +4 is to lose electrons. So we have loss of electrons here. This is oxidation. How many electrons does 10 lose? 4, right? So we go from 0 to +4. That's because we lost 4 electrons. So this is oxidation. Who's been reduced? What atom? Who has decreased their oxidation state? Nitrogen, right? So nitrogen goes from a +5 to a +4. Specifically, how many electrons has it gained? 1 electron. So gain of 1 electron, that is reduction. Okay, so now let's go ahead and try that. So this is an easy one, very easy. Elemental forms, compounds. I want to know, I forget what I asked, but I probably asked something about oxidation and reduction. do I actually ask in this question? Who do I ask first? I ask for oxidation or reduction? Oxidation, and then I ask for reduction. And then what do I ask for the last thing?
Oxidizing agent.
Okay, oxidizing agent. Okay, so go ahead and get your answers in if you haven't. So if you assigned oxidation states correctly, you would find that aluminum goes from a 0. What does it go to? What is aluminum in the product? What is its oxidation state? Should be a +3. So if it goes from 0 to +3, that means it lost electrons, specifically 3 of them. So this guy was oxidized. And then oxygen, what is oxygen, diatomic oxygen? What is the oxidation state of this guy? This is 0, it's the elemental form. When it goes to make this compound though, what does it change to? Plus or -2, right? So we go from a 0 to a -2. The only way we can do that is by gaining electrons. So this is our reduction. Okay, so then finally, what did I ask? I asked about who is the oxidizing agent. So who is the oxidizing agent here? Who is the agent of oxidation? Oxygen, right? It's the thing that itself was reduced because it went out, it stole electrons from somebody, it oxidized something, and it reduced itself. Okay, so oxidizing agent is one of the best oxidizing agents out there. This is oxygen, where it gets its name. Oxidation gets its name. Okay, so really quickly, we'll see how we go. I'm going to start talking about how to balance. What are we talking about? I'm going to start by talking about how to balance redox reactions. Okay, so we have been balancing reactions thus far all the time in chemistry. We have not yet balanced a redox reaction. And there's a reason for that, because they're a little bit more complicated than balancing normal reactions. Before we can do that, we need to introduce you guys a concept of a half reaction. Okay, so in a redox process, we always have to have reduction come with oxidation, right? If somebody loses electrons, somebody has to gain them. Okay, so we essentially usually write these guys together. We're going to start by writing these, or we're going to start writing these in these chapters by splitting them into their separate half reactions, where we write the oxidation process as its own little half reaction and the reduction process as its own little half reaction. Okay, so for this little reaction that we have here, we've got aluminum, which has a 0 oxidation state. As a reactant, it goes to a 3+ or a +3 as a product. So in this process, we know that aluminum is oxidized. Okay, when we write that as a half reaction, just the oxidation half reaction, we're going to write aluminum, right? But what are electrons in this overall process? If we're being oxidized, are electrons considered a reactant, or are they going to be a product? If you go from a neutral molecule, aluminum 0, and you go to aluminum 3+ as a product. So what else is going to be a product in that overall reaction? The electrons, right? And so for oxidation half reactions, we always write the electrons as a product, right? Because again, we're losing them in this overall reaction, we consider them a product. For this reaction, aluminum goes from 0 to 3+, so it loses those 3 electrons. And we're also going to balance that with respect to charge. On the other hand, we've got copper. Copper goes from a +2 to a 0, so it gains electrons. In getting from +2 to 0, how are we going to consider the electrons in this process? Are they a product here too, or are they going to be a reactant? So for reductions, we're going to consider electrons as reactants, right? This guy, copper 2+, has to gain 2 electrons to get to copper solid, which is the product, okay? So for oxidation half reactions, we're going to write electrons as a product. Reduction half reactions, electrons are going to be a reactant, okay? Okay, so now that we have the concept of half reactions, let's start balancing redox reactions, okay? So there are 2 inherent difficulties in balancing redox reactions. Number 1, you have to balance with respect to mass, which we have kind of already been doing thus far. The other thing that you have to consider, though, is you also have to balance with respect to charge. So it adds a little extra level of difficulty when we actually go about balancing these reactions. So we're going to follow a couple different steps in actually doing this, okay? The first thing that we're going to do when we're trying to balance a redox reaction is we're going to assign oxidation states. And the reason why we're going to do that is because we still need to figure out who's being oxidized and who's being reduced, okay? Once we know that, we are then going to split up our oxidation process into its own half reaction and our reduction process into its own half reaction. We are then going to balance those individual half reactions exclusively, not together, okay? We're first going to balance with respect to mass, okay? So the first thing we balance is any elements other than hydrogen and oxygen. If we need to add oxygen, we're going to add it in the form of water. If we need to balance H's, because of that, we're going to add them in the form of protons. And then there's going to be another little added step if this occurs in a basic solution. And we'll get to that whenever we go over it. Once we've balanced with respect to mass, we're also going to balance with respect to charge. So we're usually going to have to multiply the reactions by some number to get the overall electrons transferred the same. Once we do that, we can add up everything, and we are usually done with the process, okay? So I want to do one of these, just to kind of get the ideas flowing and get the actual illustration of this process down before you leave. So in this overall example, we want to balance this redox reaction in an acidic solution, okay? The first step that I'm going to do in doing this is I'm going to figure out who's been oxidized and who's been reduced, and I'm going to utilize oxidation states to do that, okay? So if I look at copper, copper's nice and easy. It has an oxidation state of 0. If I then move on to NO3-, oxygen is the more predictable molecule here. It's going to have an oxidation state of a -2. So because of that, nitrogen is going to have an oxidation state of a +5 in this molecule. When I go to my products, I have copper with a +2 oxidation state, and then oxygen again will have a -2. Nitrogen now has a +4, okay? So in going from a 0 to a +2, what has happened to copper? It has been oxidized, okay? Specifically, how many electrons has it lost? 2, right? So we're going to write that as the oxidation half reaction, as its own little separate thing. So in the oxidation half reaction, we have copper going to copper 2+, and we're going to write the electrons as a product, okay? Now, same thing, we have the reduction process. Who's been reduced in this overall reaction? We go from nitrogen, which has a +5, to nitrogen, which has a +4. So that guy has been reduced. We will write that as our reduction half reaction. How many electrons has that one nitrogen gained in going from a +5 to a +4? We have 1 electron gain, right? So we're going to write that in our reduction half reaction as a reactant, right? Electrons our reactants and reductions. So we have NO3-, it gains that one electron to form NO2. Okay, that's number one, separate the two half reactions. Now we're going to balance with respect to mass. The first thing we look at is any element other than oxygen or hydrogen. For our oxidation half reaction, do we have any element other than copper? Electrons don't count, so just ignore them. Right, so we only have copper. Is copper balanced with respect to mass here? We have a 1 and we have a 1, so are we good? Yes, okay, so we move on. Oxidation half reaction is done. Now, when we come over here to the reduction half reaction, we start with everything other than hydrogen and oxygen. What is the only other element that's in this thing? Nitrogen. On our reactants, we have 1 nitrogen. On our products, how many nitrogens do we have? 1. Okay, so nitrogen is balanced, and I want to get rid of the 1 because it's going to confuse me. Now, we balance with respect to oxygens. That's what we move to next. The problem is we have 3 oxygens over here. We have 2 oxygens over here. So to get another oxygen into this overall reaction, we're going to add however many waters we need to get however many oxygens we need in, right? So we have 3 versus 2. I only need to add 1 water. Who do I need to add it to, though? To the products, right? Because we only have 2 oxygens over here. If I add a water, that will give me 3 oxygens. So I'll be balanced with respect to oxygens. But now what is the problem? I have introduced 2 hydrogens, okay? So to balance those, all we have to do is go back over to our, to our reactants and add an equivalent amount of protons, okay? So now, if we've added our protons, we've added our waters, everything is balanced with respect to mass. The last thing we have to do to recombine these is we have to balance with respect to charge. So in this overall process, in our oxidation, we have a 2 electron transfer. What about our reduction, though? How many electrons do we transfer in this reaction? Only 1, okay? So we need to multiply this reduction process by a number to get the same number of electrons. What number should I multiply my reduction half reaction by to get the same 2 electrons? 2, okay? But the thing is, I have to multiply everything by 2. So that means my protons, I end up with 4 protons. Everything has to be multiplied by 2. 2 electrons goes to make 2 NO2 plus 2 H2O. Now that we have balance with respect to charge, we get to add them together. Okay, so we bring down our oxidation. We've got copper going to make copper 2 plus 2 electrons. When we add these guys together, what's going to cancel here? The electrons are going to go away, right? We've balanced with respect to charge. And so now we are left with our balanced redox reaction. 4 protons plus 2 NO3- goes to make 2 NO2 plus Cu2 plus 2 H2O. Just make sure that I've caught everything. This guy, this guy, this guy, this guy, this guy, this guy. Okay. So that is balanced. Okay, so start with oxidation states. We split them up into their 2 half reactions. We balance with respect to mass first, then we balance with respect to charge. Okay, that's all I have. So let me know if you guys have any questions with respect to the exam on Thursday. Let me also know if I missed a number, because that could happen very easily. This one. Last week, so that's what we ended on. And I had gone really quickly through how to balance a redox reaction, right? So we're going to start with that today. But with respect to balancing redox reactions, we have to take into account not only balancing the reaction with respect to mass, which is what we've normally done, but also balancing the reaction with respect to charge, which is what essentially we have to add in balancing these redox reactions. I had also talked about how the process differs depending on the type of solution we're in, right? So the first example I gave you was in an acidic solution. There is a little bit of an extra step if we're trying to balance a redox reaction in a basic solution, okay? So I did have the acidic solution, that example we did get through last week, so I'm going to start here. But if you need to just kind of refresh yourself with respect to the acidic solution, we'll get through most of this. It's all pretty much the same. There's just one little added step, okay? All right, so let's go ahead and start. We're balancing the following redox reaction, and this is in a basic solution. So the first step in this is, again, figuring out what's been oxidized and what's been reduced. And to do that, we have to assign oxidation states, right? So we go through and we assign oxidation states to all of the atoms and all of the compounds. So for example, if we start out with ClO-, what is the oxidation state in this compound for oxygen? Or who is the more predictable of these two atoms, chlorine or oxygen? Oxygen, right? It has an oxidation state usually of a -2. And chlorine plus oxygen, what do they have to sum to? The -1 overall, right? So because of that, chlorine in this compound, what oxidation state does it take on? It would be a +1, right? So we have a +1 for chlorine, a -2 for oxygen. We move over to the next compound. We have a big chromium with a bunch of hydroxides in it. So because of that, I'm going to go ahead and say that chromium is the least, Chromium is the least predictable. Both oxygen and hydrogen are more predictable than it. Again, overall, this guy has to sum to a -1. There are 4 hydrogens and 4 oxygens. So we have 4 times a -2 plus 4 times a +1 plus X overall. So when we solve for this, what does chromium have to be to balance this? X minus 8 plus 4 equals -1. So chromium has to be a +3 here. So we have a +3. Oxygen, again, with a -2. Hydrogen with a +1. We move over to the products. We'll start with the easy one, just chloride, the monatomic ion. What is the oxidation state for Cl-? Just a -1. And then for this compound, again, we have oxygen and chromium. We have 4 oxygens. It's more predictable. They have to sum to a -2 overall. So what does the oxidation state of chromium have to be here? X plus -8 equals -2, so we have to have a +6. Okay, so that's number 1. We have to assign oxidation states. That's going to tell us what's been oxidized and what's been reduced. It's also going to tell us by how many electrons. Okay, so in this reaction, what atom has been oxidized? Who has increased their oxidation state? So chlorine's gone from a +1 to a -1, so we see a decrease in oxidation state. Chromium has gone from a +3 to a +6, right? So we see an increase in oxidation state. So that is oxidation. So oxidation here, and I'm going to go ahead and write out my separate oxidation half reaction, because that's step number 2, is writing out these half reactions. So for an oxidation half reaction, are electrons a product or are they reactant? So we'll go ahead and write out chromium, OH4- going to CrO4-2-. If you're oxidized, you lose electrons, so would you think electrons would be a product or a reactant here? You lost them, they've gone away, so now they are unfortunately a product, right? So specifically, if we went from a +3 to a +6, how many did we lose? 3 electrons, right? So that's a good purpose with respect to oxidation state. It doesn't just tell you who's been oxidized and who's been reduced. It also tells you by how many, okay? So the oxidation half reaction, we have our chromium hydroxide compound going to this guy and 3 electrons. And then we'll do the exact same thing for the reduction half reaction. So we'll zoom in over here. And our reduction half reaction, who's been reduced here? It's chlorine, right? So we'll go ahead and write out chlorine, ClO-. For reductions, electrons are going to be a reactant, right? You have to gain them to get to your new oxidation state. How many electrons did chlorine gain in going from a +1 to a -1? Gain 2 electrons, right? So we'll have this guy plus 2 electrons going to make our Cl-, okay? So first step, assign oxidation states, and then write out the 2 separate half reactions, okay? Now we have to go through and balance each half reaction with respect to mass first, okay? So I'm going to start with our oxidation half reaction. So we're going to balance any atom other than oxygen and hydrogen first, right? The only thing that is not oxygen and hydrogen in this overall half reaction is chromium. Is it balanced right now with respect to mass? I have 1 chromium over here. I have 1 chromium over here. Am I good? I'm good with chromium, right? Now we're going to balance oxygen and hydrogen, okay? For our reactants, we have 4 oxygen. For our products, we also have 4 oxygen. So are we good with respect to oxygen? So now, what do we not have balanced? Hydrogen, okay? We are going to balance hydrogen by adding protons, right? To whatever side we need to actually balance the hydrogen. So right now, I have 4 hydrogen as an oxidation. To balance that, I'm going to divide my little line here. I'm going to add 4 protons to my products, okay? That is to balance hydrogen. Now, because we are in a basic solution, this one little extra step that we have to take into account is we have to neutralize any type of protons we added. And we have to do that via the inclusion of hydroxide ions, okay? So if I want to neutralize these 4 protons, I need to add an equivalent amount of hydroxide, which is fine, but if I did it to that side, I also have to go back and do it to the other side, okay? So if I added 4 hydroxides to the product, then I also have to go over and add 4 hydroxides to the reactants, okay? All right, so then what are we left with? So we'll go ahead and rewrite this guy as 4OH- plus Cr OH4- going to CrO4 2- plus 3 electrons, and then 4H plus 4OH-, what does that make if we combine them? H plus OH gives us what? Water, right? H2O. So this would give us 4H2O. Again, the inclusion of the hydroxide was to neutralize the protons. Okay, so now, unfortunately, we have to do the exact same thing with respect to the reduction half reaction. 4 minus. All right, so again, we start with balancing any atom besides oxygen and hydrogen. The only other thing there is chlorine. They're balanced, right? We have 1 and 1. Now we're going to balance the oxygens. Are they unbalanced as is written on our reduction half reaction? Right, we have 1 oxygen as a reactant, we have 0 as a product. So to get in oxygen, we are going to add it in the form of water, H2O, okay? Now, because we've included H's in that H2O, we have to balance the hydrogens that we've just added. We're going to do that via the inclusion of protons. So we'll add in 2 protons here. But now, again, because we're in basic solution, what do we need to do to get rid of those protons? We're going to add an equivalent amount of hydroxide. So we're going to add 2 OH-, but if I do it over here, I also have to do it over here. Okay? So when these guys come together, we've got H plus OH gives us 2 H2O plus ClO- plus 2 electrons goes to Cl- plus H2O plus OH, or 2OH. Just as a note, we have a water and we have 2 waters, right? Those are going to cancel, or at least one of them. So we're going to take away this 1, and we're going to get the right eraser, and we're going to take away one of these guys. And again, we're going to get the right eraser. Plus 2 OH-. Anything that shows up as a product and a reactant, you're going to cancel. We had 2 waters as a reactant. We had 1 as a product. So one of those will cancel. Okay, so that is it with respect to mass. We're balanced with respect to mass. Now we just have to bring these guys back together and balance with respect to charge. Okay, so in our first reaction, our first reaction, we had a 3 electron transfer. In our reduction reaction, we had a 2 electron transfer, right? We have to get those electrons to be the same. So we need to multiply these guys by whatever number we need to make sure that they're transferring the same number of electrons. So for my oxidation, what should I multiply this whole reaction by so that I have like some sort of whole number multiple between 2 and 3? I need to multiply this guy by 2 because our least common multiple is going to be 6. So that's going to give me 8 OH minus plus 2 CrOH4 minus, going to make 2 CrO4 2 minus plus 6 electrons plus 8 waters. 8 waters. So this is my oxidation half reaction. Now, what do I need to multiply my reduction half reaction by for the same exact purpose? I need to multiply this guy by 3, right? Because we need 6 electrons total. So then for my reduction, I'm going to have 3 H2O plus 3 ClO minus plus 6 electrons, going to make 3 Cl minus plus 6 OH minus. Yep, okay. So now they're balanced with respect to charge. We just have to add them together, okay? So anything that shows up as a reactant as well as a product is going to cancel. So my first notice of that is the waters, right? So water over here, we have 3, we have 8, right? So we're not going to be left with 3 and 8. We're going to be left with 0 over here. And then we're going to be left with 5 over here. Is there anything else that would cancel? The OH minus. So we're going to get rid of these guys entirely. And we're going to be left with 2 over here. And then what else? The last thing. The electrons, right? So the electrons are just going to cancel one another when we add. And so we are left at this point in time with 2 OH minus plus 2 CrOH4 minus plus 3 Cl minus, this guy, this guy, this guy, goes to 2 CrO4 plus 3 Cl minus and 5 waters. So lots of little nitpicky steps. And again, the only difference between what we did last week and what we did this week was the inclusion of the hydroxides to neutralize any type of protons that were present, because again, this is going to occur in a basic solution as opposed to an acidic one. Okay, so I want you guys to try one of these on your own. So the next slide is a question. I want you to balance the redox reaction that I give you in an acidic solution. The only thing I want to note is what the oxidation states are. So I want to give you guys the oxidation states and then let you go ahead and balance it. So for this, we have a +6 for chromium, a -2 for oxygen, a -1 for chlorine, +3, and a 0. And the big important thing to note here is that sometimes when you balance electrons originally, you'll also balance the mass of things. So just think about that as you go through this. But go ahead and try it, and then I have a question on Socrative when you think you're complete. Okay, so let's go ahead and talk about this one. Some of you haven't gotten an answer in, but I do want to move on. So first step in this is separating our two separate half reactions. We have the oxidation state, so who is being oxidized in this reaction? The chlorine, right? So chlorine, Cl minus, is being oxidized, right? So we're going to write the electrons as a product here. But most importantly, for each chlorine, how many electrons is it losing? Because the Cl2 is going to have an oxidation state of 0. That's for each separate chlorine, right? So if we're going from -1 to 0, how many times do we do that if we go from a Cl to a Cl2? We do this 2 times, right? So this is kind of the trick in this little question here. So chlorine going to a Cl2, each chlorine itself is going to lose 1 electron. So when we balance it with respect to 2, the overall loss is 2 electrons, right? Each individual chlorine is losing 1 electron. Same exact thing for the reduction, right? So for the reduction, we're reducing chromium. Chromium 2O7 2-. For each individual chromium, we're going from a +6 to a +3. So for each chromium, how many electrons are they gaining? 3, right? But how many times do we have to do it? How many chromiums are there? 2, okay? So because of that, if each chromium is gaining 3, we need to do it twice, then the balanced redox reaction, just for the half reaction here, would be Cr2O7 2- plus 6 electrons going to 2 Cr3+. Okay? So this is what I said originally. I know it doesn't make sense when I say it initially, but sometimes balancing with respect to mass will balance with respect to charge for the initial half reactions. Okay? So then, balance, we have our little half reactions. Now we have to balance with respect to mass. For the oxidation half reaction, do we need to balance anything? We have 2 chlorines, so everything's good there. Now for the reduction half reaction, what do we have to be concerned about? We've got 2 CRs, that's fine. What about oxygens though? So we have 7 oxygens as a reactant. We need to add 7 as a product. How am I going to do that? Through water, right? So first step is always balancing oxygen. I'm going to add an equivalent amount of water to balance the oxygen that I need. Because I've done that, I've added 14 protons. What do I need to do now to the reactant side to balance the H's? I need to add 14 protons. So 14 H plus is going to balance the hydrogen that I just added in water. So this is an acidic solution. We don't have to make that last step with the hydroxide, so we're done, right, with respect to balancing mass. Now we can bring them together, and all we have to do is be concerned with balancing with respect to electrons, okay? So for our reduction reaction, we have 6 electrons. For the oxidation, we only have 2. What do I need to multiply my oxidation reaction by to get 6 electrons overall? I'm going to multiply this guy by 3. That's going to give me 6 Cl minus goes to 3 Cl2 plus 6 electrons. I'm now going to add to that my reduction half reaction. We have 14 H plus Cr2O7 2- plus 6 electrons goes to make 2 Cr3 plus 7 H2O. What cancels here? The only thing that cancels when we add these two are just the electrons. And so finally, we have our 14 H plus Cr2O7 2- plus 6 Cl minus goes to make 3 Cl2 plus 2 Cr3 plus 7 H2O. This. So much fun, right? So what's nice about these is they're just rules, right? It's just a sequence of events that you have to follow. So it's not super conceptual, but it's a hassle, so I apologize for that. Okay, so that's like the introduction to the chapter, right? It's reminding you on how to balance or how to do oxidation states, how to determine whether something has been oxidized or reduced, and then we do introduce you to how to balance these overall redox reactions. Now we're going to actually get in to the meat and potatoes of the electrochemistry chapter, which is dealing with electrochemical cells, okay? All right, so let me introduce you to a redox reaction that's nice and simple, okay? So let's say we have zinc, and it's solid, and it reacts with copper 2+ ions, and it is oxidized in the process. It's going to transfer its electrons to copper, reducing it, forming copper solid, and then it's going to be oxidized, so it's zinc 2+, okay? Okay, so this is a nice, spontaneous redox reaction. We have zinc being oxidized, it's reducing copper, great, overall, okay? All right, so in this process, what's actually occurring, right? At the molecular level, if we zoomed in, we would see an electron transfer take place between zinc and copper. Zinc is directly transferring its electrons, moving its electrons to these copper ions that are floating to the surface of our solid zinc, okay? So movement of electrons, transfer of electrons, it should sound ideally somewhat familiar to you. Where else do we see movement of electrons? Not in chemistry, but in just normal everyday world, real life world. Electricity, right? Electricity is the movement of electrons, okay? So, because we actually see the transfer of electrons in redox reactions, they have the potential to generate electricity or to generate electrical current, okay? But as is, right now, this redox reaction is not going to be able to generate any type of electricity because these electrons are being directly transferred from our metal, which is zinc, to the ions in solution, okay? So to get this to actually do something, to generate electrical current so that we can power a light bulb or do whatever, we need those electrons, instead of going directly between the two, to go through some sort of external conductive wire, okay? How are we going to do that, though? How can we manipulate the system to get those electrons, instead of being just directly transferred, to go through some sort of conductive wire before they actually do their reaction? So what we could do is we can separate these two reactions into their two separate half reactions, right? So we can take zinc metal, and we can put it in a solution of zinc 2+ ions. And then we can take copper metal, and put it in a solution of copper 2+ ions. We have separated the two half reactions, right? If we go back to that spontaneous redox process, who is going to be oxidized, or who was oxidized in the spontaneous process that I just showed you? Zinc or copper? So zinc, in that spontaneous redox process, was oxidized, right? So we see this oxidation down here. As a reminder, with respect to oxidations, electrons are products. On the other hand, copper is going to be reduced. So this is our reduction half reaction. And again, electrons are reactants for reduction, okay? So again, we have separated these two half reactions. We put zinc in a solution of zinc ions, copper in a solution of copper ions. We still need electrons to flow, right? So now, copper still wants to take those electrons from zinc. How are we going to let zinc give up its electrons? Right now there's just empty space or air between the two. So what do we need to do to make sure we actually get movement of electrons and we get electricity? We just need to connect them, right? If we connect them via some sort of conductive external circuit, this spontaneous redox process will still occur, right? Zinc will still give up its electrons. It will still be oxidized to these copper ions, producing copper solid on the surface of our little reduction half reaction, okay? So this is kind of the basis behind all of electrochemistry, especially with respect to what we're going to be studying, which is voltaic or galvanic cells, okay? So voltaic or galvanic cells are going to be utilizing spontaneous redox processes, which we just saw, to generate electrical current, okay? Now, a couple of things to note here. The overall construction that we have made is what we call an electrochemical cell. And again, this is a voltaic, or another word for this is a galvanic cell. Again, we're going to be producing electrical current through this spontaneous redox process. There is another type of cell, which is called an electrolytic cell. So a second type of cell is called electrolytic. And in electrolytic cells, we actually utilize current. So we use current to drive non-spontaneous reactions, for non-spontaneous redox reactions. Let me just erase my ugly little form, okay? Okay, we're not going to talk about electrolytic cells. I tend to focus exclusively on spontaneous processes or voltaic cells. So this is it. This is kind of the basis behind it, right? There's a couple things missing, and we're going to kind of derive those other things as we move through the next few slides. Okay, so first off, why does this occur to begin with? Why do we see electrons flow from zinc to copper? So this kind of goes back to stuff that we learned in 151. So in 151, you may have learned about the activity series, right? So active metals were things that love to lose their electrons. In reality, all metals have a tendency to ionize, right? So if we put zinc solid, in a solution, just any type of solution, it will have a tendency to ionize on its own, meaning give up its electrons and form its little zinc 2+ ions, okay? If it's by itself, just alone, it's going to do that and it's going to come to equilibrium, right? When it comes to equilibrium, all of those electrons that it essentially lost in this ionization reaction are going to be stored on what we call the electrode, right? So the electrode is a conductive surface. This tends to be the actual metal of the reaction. But again, it's going to be the conductive surface by which we have electrons either leave or enter our cells, okay? Okay, so again, we have zinc by itself. It ionizes on its own, and all of those electrons that it loses in this process of forming our little zinc 2+ remain on our little zinc metal electrode, okay? Same exact thing happens with respect to copper, right? But copper doesn't do it as much, right? It doesn't have as great a tendency to ionize on its own, meaning that it has less electrons and it produces less of these copper 2 ions in solution, okay? If we go back to equilibrium, the equilibrium for this overall reaction for zinc is much, much, much greater than it is for copper, okay? So this is before we've done anything. This is before we've connected these two via any type of external wire, okay? Now, if we look at this, we have a large electron buildup on our zinc electrode, and we have a very small electron buildup on our copper electrode, okay? And again, this is going back to this tendency to ionize. If we connected these two, what do you think is going to occur? How happy do you think these electrons are to be around so many other negative charges? Not very happy, right? Negative things don't like to be around other negative things. So if they're given the option, what do you think they're going to want to do? Leave, right? They're going to want to leave if they can. How can they leave? If we added a nice little thing by which they could exit, they would leave, right? These electrons that are on our little zinc electrode, before anything happens, before we ever connect them, we call them high potential, right? High potential energy because they're around a lot of other electrons. They have a lot of potential energy. They want to get out of it as quickly as possible. On the other hand, the copper electrode, because there's less electrons built up, have a lower potential energy, right? And so when we connect them, we're going to see our electrons spontaneously leave our zinc because they're at a high potential energy, and they're going to go to the copper, which is at a lower potential energy, right? That's number one, right? That's the initial movement of electrons. But why do we continue to see current flow? Why do we continue to see the movement of electrons? So if we go back to these reactions that we were looking at, right, we had high potential electrons on our zinc electrode, we had lower potential electrons on our copper electrode. When we connected the two, they were going to go from high potential to low potential. But why do we continue to see this current flow? So imagine initially these guys were at equilibrium before we connected them, right? They had come to equilibrium. When we connect them, what's that going to do to the equilibrium? Right, because electrons are part of this overall reaction, right? If they are leaving our oxidation half reaction, they are being removed from our oxidation half reaction, what is this equilibrium going to want to do to essentially replace the electrons that it's losing? It's going to shift to the right, right? So why do we continue to see electrons flowing? Because we're removing them, and so the equilibrium for this reaction is going to want to shift right to replace what it just lost, right? On the other side, we've got the opposite thing happening, right? We've got copper, which is gaining electrons. Which way is this reaction going to want to shift? Because we're adding a product. It's going to want to shift back to the left, meaning it's going to want to reduce these copper ions and form copper solid, okay? So again, it's this difference in potential energy that gets the electrons flowing. We call that electron motive force, but it's the disturbance of equilibrium that keeps it going overall, okay? So a couple of things to note here. Again, we already defined what an electrode is, right? These electrodes are our conductive surfaces. They tend to be the overall metals that are participating in the redox reaction. We have special names depending on what the actual electrode is reacting with, right? So the oxidation electrode, we call this guy the anode, right? And the reduction electrode, the metal at which the reduction is occurring, we call this the cathode. For the anode, we denote this usually via this little negative sign, and for the cathode, we denote it via our little positive sign, right? This negative and this positive comes back to the original distribution of electrons. On the anode, we had a very large buildup of our negative charge. That's why we call this negative versus the cathode, where we had less negative charge. That's why it gets the positive overall sign, okay, before anything has happened. Okay, so that's good. We've got electrons flowing. We're disturbing equilibrium, so they continue to flow, continue to flow, continue to flow. There's one little problem still. So if we go back to this overall reaction, right, we'll start with zinc. Zinc is being oxidized. We're forming our zinc 2+ ions. We're losing our electrons. We're going over to the copper one. As this reaction continues to push right, what are we producing a lot of at this point in time? We're producing a lot of zinc 2+, right? Specifically, what type of charge is going to be forming in that overall half cell? Bunch of positive charge, right? Because as this reaction is shifting to the right, we're losing electrons, but we're also producing a lot of this guy, right? And this guy has a charge to it. It's got a 2+ charge. So as this reaction continues to occur, we're going to build up a lot of positive charge over on this half cell. On the other half cell, the reverse is happening, right? On the other half cell, we are pushing this reaction back to the left, right? What are we losing in the process? We're losing this guy, right? So we're losing positive charge. What is that analogous to? If we're losing positive charge, it's kind of like saying we're gaining negative charge overall, right? So as we move through this process, we're going to start developing a bunch of negative charge over here because we're essentially making solid copper out of our 2+ ions. We're losing our 2+ ions. How long do you think that's going to go on? Right? Buildup of charge was the reason why we initially saw the electrons flowing from our zinc to our copper. So how long do you think we're going to allow this to just start building up positive charge on one side, negative charge on the other? Not long, right? So this is not going to last for long. In fact, if you connect two half reactions, we'll initially get a small little voltage, but then they will stop because of this charge buildup, right? So to complete the circuit, if we're looking at this in terms of circuits, what we add is something called a salt bridge, okay? So a salt bridge is going to be some sort of nice little porous conductive material, and in it is going to be some sort of inert salt, right? So what do I mean by inert? It's not actually going to participate in any of these reactions. It's just going to be a means by which we can get ions into solution, okay? Okay, so let's say that in this salt bridge we have potassium nitrate, okay? So potassium nitrate has two different ions to it. It has a positive ion and it has a negative ion. If we have been building up positive ion, positive ion, positive ion, which ion of the potassium nitrate is going to want to go over there to essentially neutralize the charge buildup? The positive or the negative? Negative, right? So what do we call negative charge ions? Anions, right? So this is where the anode gets its name from. It is the electrode to which the anions migrate to from the salt bridge, okay? On the other hand, if we go over to our little cathode, right, we had a buildup of negative charge, negative charge, negative charge. Which ion's going to want to migrate over there, the positive or the negative? The positive charge ions, again, to neutralize the negative charge that's building up. What do we call positive charge ions? Cations, right? So the cathode gets its name cathode because it is the electrode to which the cations migrate to. Okay, so once we include the salt bridge and we can neutralize these charge buildups via these little ions in solution in our little salt bridge, then we have completed the circuit and we have completed our little voltaic or galvanic cell, okay? Now, that is the basis. We have to talk about a couple little more logistical things, okay? Okay, so first off, what's going to be flowing between our two different half reactions in our little electrochemical cell is going to be electrical current, okay? So most of you, or at least myself, I didn't have a great background in understanding what current was because I'm not super physics-based, but current is essentially just a measure of electrons flowing. It's like a rate, right? It's a measure of charge per unit time, okay? We measure current in a unit called ampere, or we call this amps very frequently. An ampere is defined as 1 coulomb per second, okay? And a coulomb, this big capital C, this is just a unit of charge, okay? So this is a charge per time. Electrons have a certain amount of charge to them. So what an ampere tends to be overall is 6 times 10 to the 18th electrons per second, okay? So 1 amp is that many electrons flowing per second. And again, current is a rate. Or, yes, we'll just leave it like that. Okay, so that's what's going to be flowing, right? Electrons moving between our two half reactions. And we're going to measure that via electrical current. We measure that via amps. A couple of things. So now, we kind of compare this rate of electron movement, or this current that is produced, to water flowing down a mountain, okay? So let's imagine that you have a stream and you have water in it, right? Why does water flow down a mountain? What does that do to? Differences in what? Potential energy, but what type of potential energy? Gravitational potential energy, right? So water flowing down a mountain flows down because of differences in gravitational potential energy. Water will flow from high gravitational potential to low gravitational potential energy, okay? Now, what kind of affects this overall rate of water flowing? If we had a steep mountain, so a very steep mountain like this, versus a shallow mountain, who would have water flowing faster, or the faster rate of water flow? The steep mountain, right? So steeper with respect to a mountain, the faster the rate, okay? What does that mean in terms of gravitational potential energy? What does a steep mountain have a lot of, or a large difference in? It's got a large difference in gravitational potential energy, right? So that means that the larger the difference, so larger gravitational potential energy, the faster the flow of water. Okay? Okay, so current is like flow of water. It's like the flux of water through a stream, okay? Except now, when we're dealing with these electrochemical cells, we're not looking at differences in gravitational potential energy. Instead, we're looking at differences in electric potential energy, right? So the larger the difference in electric potential energy, so larger the difference here, the more current we're going to see, right? So more current is due to larger differences in electric potential energy. Where are these differences coming from, though? Where does this originally come from with respect to our little electrodes? What was generating that electric potential energy, or that high potential energy on the zinc electrode? It all goes back to that tendency to ionize, right? Zinc had a larger tendency to ionize, so we saw a larger buildup of electrons on that electrode because of that. That's what gave them that high potential energy, okay? So how do we measure these electric potential energy differences? Well, we use something called the volt, right? So the volt is defined as 1 joule of potential energy per unit of charge. The unit of charge is, again, the coulomb, okay? Okay, so again, the larger the potential energy differences, the more current we're going to see, and we measure that difference in potential via something called the volt. So now let's take this. This is not the Chevy volt either, unfortunately, which is kind of is, I guess. But so now let's take this back to our electrochemical cell, okay? So in our electrochemical cell, we again have our two separate half reactions. We have our two separate half cells. We have our oxidation half cell, which is where the anode is. We have our reduction half cell, which is where the cathode is. We will measure this difference in potential between these two separate half reactions via something called a voltmeter. So a voltmeter can measure this overall potential difference between our two separate half reactions, and what that is called is the overall cell potential. And we abbreviate this E cell, okay? If all our reactants and products are at standard state, then this gets another special name, which is just E naught cell, because again, the little naught tells you that everything is at standard state. What this cell potential is trying to measure is the difference in potential energy between the two separate half reactions, right? We call this the cell potential, and we abbreviate this little E cell, but in reality, this should be a delta E, right? We're looking at a difference in potential between two separate things. By convention, we don't use the delta for whatever reason with respect to electrochemistry, but this really is a delta. We're looking at final minus initial, okay? So again, delta E is just final minus initial. And overall, what we're going to see is if we get a cell potential, an E cell, that is positive, this is due to a spontaneous redox reaction, a spontaneous process. And the larger and more positive this is, larger and more positive, the more current we're going to produce. Again, going back to this difference in potential, the larger difference in potential, the larger the voltage. Okay, all right, so let that sink in for a second. Let's go ahead and do a quick little conceptual question. So in a voltaic cell, I want to know which one of these occurs. Okay, so 69% correct rate. Get reports, download. Okay, so what is the correct answer here? In a voltaic cell, electrons flow from what to what? Negatively charged electrode to the more positively charged electrode. Again, this is from the anode to the cathode. The anode had the negative charge because it had a larger charge buildup, a higher potential energy initially than the cathode. Okay, so a couple more things that I'm going to breeze right through. More logistics, okay? So with respect to these electrochemical cells that we've been drawing, it's really kind of tedious to sit out and draw all of these various electrochemical cells, right? You have your little half reactions, your little metal electrodes, etc., right? So we have a shorthand method of essentially trying to depict these overall electrochemical cells, and it follows the following convention. So we start on the left-hand side with the oxidation half reaction, right? So this is going to be our oxidation half reaction, or our anode cell. And then it moves as we go from left to right to the reduction half reaction, or the cathode, what is taking place at the cathode, okay? And it follows the general convention of the oxidation electrode, followed by electrolyte, and then the reduction electrolyte, followed by electrode. Anytime we change phase, we depict that via just a single line, right? So what do I mean by change phase? As we go from zinc solid, which is our anode, what do we do when we go into zinc 2+? What have we done? We had a solid, now what phase are we in? Aqueous, right? That's a change of phase. That's what you're going to utilize to denote that there's a change of phase. You use a single solid line. Anytime there's a salt bridge connecting the two separate half reactions, we use this little double line instead. Okay, so again, the anode, the electrolyte, we separate it via a single line, salt bridge with the two lines, the cathode electrolyte, and then the cathode itself. And again, that's going to tell you essentially what's happening in the overall voltaic cell. Okay, so that's great, neat. Moving on. Now, typically, with respect to redox reaction, the anode, the electrode at which oxidation occurs, tends to be the metal that is actually oxidized, right? Whereas the cathode, which is the electrode at which reduction occurs, it tends to be the metal that is actually reduced. Sometimes, though, that's not the case. We can see redox reactions and electrochemical cells that utilize reactions that don't actually include a metal at all, right? So, for example, if we utilized this redox reaction, where we have iron being oxidized to iron 2+, and then manganese, this is manganese in the +6 oxidation state, going to manganese 2+, we have the oxidation, right? The oxidation, we have our nice little anode in the form of iron solid, but where's the metal for the reduction half reaction? In the reduction half reaction, we've got this permanganate, 5 electrons, some protons going to Mn2+, and 4 waters. So where is the overall metal for this guy? There is none, right? But we can still utilize this in a nice voltaic cell. The only thing that we have to do is we have to include something called an inert electrode, okay? What we mean by inert electrode is essentially a metal conductive surface that is just a vehicle by which electrons can enter and leave whatever electrode cell, whatever half reaction they're dealing with. What we mean by inert is the fact that this is not going to actually react overall, right? So this, whatever this metal is, whatever this conductive surface is, doesn't undergo any type of reaction. It's just a vehicle by which electrons can enter and leave the cell. So this metal, this inert electrode, tends to be platinum. Platinum is a nice metal that does not participate in many redox processes. It instead can just be nice and conductive. It can transfer electrons, it can take them, whatever it needs to do, okay? So in that overall voltaic cell that I presented in the first slide, or that last slide previous, we had the iron as our oxidation half reaction, as our anode, but for our cathode, where we see MnO4 being reduced, that's going to be depicted by our platinum metal, because again, it's serving the purpose of just getting electrons into and out of the cell. So now, one little extra thing to note, if you do use an inert electrode like platinum in a reaction like this, then the only other thing that you have to change with respect to our little shorthand notation is the fact that, number one, platinum is the cathode electrode, the actual electrode that's participating in the reduction reaction. But now, for this reduction reaction, we had a bunch of stuff in solution, such as our MnO4, our Mn2+, our H+. All of those are in the same phase, right? So we can't separate those via single lines. Instead, we will separate them via commas. So anything where you have a redox reaction and you have things that are participating that are in the same phase, you just separate them via commas as opposed to the solid line when we actually change phase overall. Okay, so that's just a little note. Make sure whenever you're dealing with our little shorthand notation that you utilize those following conventions. So a couple more things before we finish tonight. We're going to go back to this idea of cell potential. Okay, so I had introduced the idea behind cell potential when we had depicted our original voltaic cell, right? So we had our two half reactions, and we measured the cell potential via our nice little voltmeter, okay? Cell potential, just as a reminder, is the measure of a potential difference between two separate half reactions, okay? It's important to note that there is not an absolute electrode potential, right? If we isolated one of the half reactions by itself, it wouldn't have a potential. It doesn't exist. It has to be in conjunction with another cell so you actually get a difference in potential between the two, okay? It would be nice, though, if we did have some sort of just singular electrode potential for all of our various half reactions. Okay, so building that a little further, what we do is what we do usually with respect to any time we have to measure a difference in something, right? So, for example, enthalpy. Enthalpy, we measure differences in enthalpy. There is no absolute enthalpy, but what do we do to kind of get around that so that we can utilize nice little tables and charts of things to calculate the enthalpy for any reaction? We define a zero enthalpy, right? What was the enthalpy that was zero for anyone? Enthalpy of formation? Anything in its elemental state, right? That was relative. We do the same exact thing here. We define, essentially, a zero with respect to reduction potential, and then we measure everything relative to that so that we can generate these nice little tabulated lists of reduction potentials and electrode potentials, okay? Now, what is our zero and standard reduction potential? It is what we call the standard hydrogen electrode. It is an electrode at which the following reaction is essentially occurring. We are seeing the reduction of protons to hydrogen gas, right? This is occurring at a platinum electrode, so our nice little inert electrode is here, and it is also occurring at standard state. So what is standard state with respect to anything in solution? We have something in solution. What's the concentration of it if you're at standard state? 1 molar, right? So this means that we have 1 molar protons. What about if you're a gas? What is the standard state of a gas? 1 atm pressure, okay? So we define this reaction where we have 1 mole of protons being reduced and there's bubbling in 1 atmosphere of hydrogen gas. This is all occurring at a platinum electrode. We define this as our zero potential, our 0 volts, okay? So this is the definition of our standard reduction potential. We use this nice little standard hydrogen electrode, or SHE. Okay, so now we take our little standard hydrogen electrode, we've made it, we've put it in our lab, and we go in and we connect it to another half reaction, right? So let's say that we connect it to our zinc electrode, where we had zinc solid in solution with zinc 2+. We connect the two together, right? And we measure the voltage. We measure the potential difference between the two, okay? So again, this potential difference, this E cell, is the difference in potential between the final half cell and the initial's half cell. And what we're dealing with respect to final and initial is in terms of the electron, okay? So we have our anode as our zinc, and our cathode is our SHE, our standard hydrogen electrode. Where does the electron end up? Does it end up on the cathode, or does it end up on the anode? It ends up on the cathode, right? So if we're measuring the cell potential, our final state, this is E final minus E initial, our final state is the potential of the cathode, right? Our initial state, where it started, was the anode. So the cell potential is defined as the potential, or the standard reduction potential of the cathode minus the standard reduction potential of the anode, okay? If we did that, we connected them, which is what we've done, and we found that our cell potential was this 0.76 volts. That's what this is, right? So this is, we've connected them, overall cell potential is 0.76 volts. Do we know, or have we defined one of these with respect to our standard reduction potentials? We've told you, or at least we've ideally told you, that this SHE, what have we defined it as? What is its reduction potential? 0, right? This, in this cell, is our cathode. So this is 0. Can we measure the potential difference, or our reduction potential for the anode from this data? We've defined hydrogen as 0. We've measured the difference in potential between a hydrogen electrode and a zinc electrode, and we've gotten an overall difference in potential of 0.76. With that, we can calculate the reduction potential for the zinc couple, which ends up being a minus 0.76 volts. Okay? So the whole idea behind this, again, is that we want reduction potentials, or kind of like a measure of the tendency to reduce things or be oxidized by things in terms of just single half reactions. We can't do that, though. We have to have differences. So because of that, or to get around that, what we have done is connected any and all possible redox reactions to this standard hydrogen electrode. We've measured the potential difference between the two, and then we've calculated the other thing from that. Okay? With that, overall, we get these nice, beautiful tables. All of these various reduction potentials, given that they have all been connected and measured relative to our 0 potential, which is our standard hydrogen electrode. Okay? So a couple of things to note with respect to this overall table, right? Up top, we have positive values. These are all positive reduction potentials or electrode potentials. Down below, we have negative values, right? What we see with respect to the arrangement of this table as is everything down here loves to be oxidized. Everything with a negative reduction potential loves to be oxidized, whereas everything up here loves to be reduced. So the more positive the reduction potential, the greater the tendency for reduction. Okay? So with respect to being oxidized, we've also defined that in a different term. If you're oxidized, what are you really good at doing? If you like to give up your electrons, you're very good at giving them to people or other things. So what does that do? If you're giving your electrons to somebody, what do we call you? We call you a reducing agent, right? So these guys love to be oxidized. They are very, very, very good reducing agents. Whereas the things that love to be reduced, what are they good at being the agent of? They're very good at being the agent of oxidation. So up here, anything with a very positive reduction potential, it's a very strong oxidizing agent, whereas things with negative reduction potentials are very strong reducing agents. And so now we have this great tabulated list of standard reduction potentials. We can calculate the overall cell potential for anything we would ever want to calculate, given that it's on this table, at least. Okay? And we will have to wait on that until next time. So again, and then we can utilize that to calculate the cell potential for anything we could possibly want given the redox reaction. Okay? So what was that standard, or that arbitrary 0 that we defined? What was the reaction? So our arbitrary 0 was the hydrogen electrode, right? The standard hydrogen electrode. And it was essentially just the reduction of protons to hydrogen gas, right? So we said this reaction is going to have a 0 volts, and we are going to measure everything relative to it, okay? So utilizing that and the fact that when we calculate these cell potentials, we're essentially taking the potential of the cathode and subtracting from it the potential of the anode, we have been able to tabulate all of the various possible half reactions that you could ever want to look at, okay? And so that is what is given in our nice little standard tables just like this, okay? So now, there's a couple of things, because we're going to be dealing with these quite a bit, so I want to introduce you to it. A couple of things to note about this little standard tabulated table. okay? These things, these actual potentials, right, are measured in volts, okay? And right now, these are all at standard state. So every time they give you a table like this, all of the reactants and products are at standard state. Again, all of these potentials are measured relative to the standard hydrogen electrode, which has this 0 volt potential, okay? Now, another thing to note about all of these guys is that they are all written as reductions, right? So this is why I tend to call these guys standard reduction potentials, because the way they're written in our little table is as reductions, even though sometimes we'll need to utilize them as oxidations, okay? So all of these guys are written as reductions. I also noted last time that everything up here with positive potentials, positive standard reduction potentials, all of these guys love to be reduced, okay? So everything that had a positive value with respect to the reduction potential relative to hydrogen loves to be reduced, whereas everything down here at the bottom of the table that had negative potentials, these guys all love to be oxidized. They love to give up their electrons, okay? So if you love to be oxidized, you're very good at being oxidized, what does that make you very good at being? So things that love to be oxidized are very strong reducing agents, right? Because if you're oxidized, you've given up your electrons, you've reduced somebody in the process, whereas things that love to be reduced are very strong oxidizing agents, okay? So given a nice list of these reduction potentials, you should be able to determine who's the stronger oxidizing agent or who is the stronger reducing agent just based off of these values, okay? Okay, so that's great. That's kind of the build. Now we're going to move on, get something different done. So again, just as a reminder, by convention, these potentials are always written as reductions, okay? So again, we'll talk about this when we utilize it, but because these potentials are written as reductions, it's going to maybe kind of confuse you just a little bit. And that's the only reason why I mentioned this, okay? Okay, so let's go ahead and try a problem utilizing these tabulated standard reduction potentials or electrode potentials, right? So let's say we have a reaction where we have aluminum reacting with nitrate and some protons going to make aluminum 3, NO, and water, okay? This is a redox reaction, and it has the potential, again, to generate electrical energy if we made a nice little voltaic cell that utilized the two half reactions that were present in this overall redox reaction. So what we're going to do now is we're going to calculate the cell potential that could be generated utilizing this redox reaction, okay? So the first step in doing this is, again, figuring out who has been oxidized and who has been reduced. So how am I going to determine who has been oxidized and who has been reduced? To determine who's the cathode and who's the anode in this overall redox process. I'm going to assign oxidation states, right? So I worry that we're not very strong in assigning oxidation states because that is going to, like, pretty much everything is built off of your ability to determine who is oxidized and who is reduced, okay? So if you feel like that is a weakness of yours, maybe you should come see me after class or something like that. Email me over the weekend, okay? All right, so if we go ahead and start with aluminum, what is the oxidation state of aluminum? 0, right? This is aluminum in its elemental form. First off, let's just instead of moving on to nitrate, let's go ahead and move immediately to the products, which is aluminum 3. What's happened to aluminum? What is the oxidation state over here in the products? +3, right? So immediately you can see what's happened in this reaction with respect to aluminum. It's been oxidized, right? It's lost how many electrons? And that's going to be an important thing. It's lost 3 electrons, right? So this guy has been oxidized, and specifically, it's lost 3 electrons, okay? So I'm going to go ahead and write out the oxidation half reaction, okay? So this oxidation half reaction, we're going to write aluminum solid going to make aluminum 3 plus 3 electrons, okay? And remember, in oxidation half reactions, electrons are products, okay? All right, so next, let's figure out who's been reduced. So I'm going to go ahead and sign the easy ones. So proton, +1, that's fairly simple, right? If we go back to our nitrate, between nitrogen and oxygen is more predictable. There are 3 of them, and oxygen tends to have a -2 oxidation state. So nitrogen is going to be whatever it needs to be for this guy to sum to the overall charge of the molecule, which is -1. So what is the oxidation state here of nitrogen? +5, right? So we'll put a +5, X is equal to, I've signed all of the reactants. Now if we move over to the products, NO, we've got a -2 for oxygen. Again, what does nitrogen have to be if it's going to sum to 0? +2. And then for water, we would have a -1, and then a 2 times a +1 equals 0. So a +1 and a -2. So who gets reduced here? Nitrogen, right? So nitrogen goes from a +5 to a +2, right? So specifically, how many electrons does nitrogen gain? Goes from a +5 to a +2. We have gained 3 electrons. So that is reduction, right? I'm going to write out the reduction half reaction. So reduction. And now for the reduction half reaction, everything's going to come with it, right? All of that leftover stuff. So we've got NO3 minus plus 4 protons plus how many electrons? 3. Goes to make NO plus 2 H2O. Okay, so what do you think the hydrogen and the waters and all of that is there? Thinking about what we talked about at the beginning of class on Tuesday, why would we need to include oxygens, or why would we need to include waters or protons or anything like that? To balance with respect to mass, right? These half reactions, they're all balanced with respect to mass, and so that's where all of this extra stuff is coming from. But this is the specific half reaction that you guys are going to have to look for, okay? Okay, so now we have written out our 2 half reactions. Now our job is to go into that table and find these particular half reactions, okay? So for the reduction one, you will find, listed in that table, nitrate plus 4 protons plus 3 electrons going to make NO and 2 waters. And you look it up, you'll find it. That half reaction has a potential of a positive 0.96 volts, okay? Then you will go in and you will look for aluminum, going to make aluminum 3 plus 3 electrons. But that would be wrong. Why would that be wrong? What are you going to find in the table? You're not going to find oxidations. You're going to find reductions, right? So if this is our oxidation half reaction, what should we be looking for in the table? Not the forward, but which direction with respect to this reaction? The reverse, right? So you should be looking for aluminum plus 3 electrons going to make aluminum solid. When you do that and you find that potential, you'll find there has a potential of a minus 1.66 volts, okay? Even though when we look and when we utilize this, it's reversed, we're not going to change the sign. We're taking it as is, specifically as written in the table, okay? Okay, so now we're at the end. The purpose of this was to calculate the cell potential. So now all we need to do is we need to take the reduction potential of the cathode and subtract the reduction potential of the anode. Again, what happens at the cathode? What particular process? Which half reaction occurs at the cathode? The reduction process. So you could also look at this as the reduction potential of the reduced one minus the reduction potential of the oxidized half reaction. So this ends up being, who's reduced here? The nitrate, right? So we have a positive 0.96 volts minus whoever is oxidized, which is the aluminum, a minus 1.66 volts. This is our cell potential. So when we add those two together, we get a positive 2.62 volts. Now again, the only thing I want to note, there's going to be a tendency to want to flip the sign of this, because again, We don't use it as a reduction, even though it's written as a reduction in the table. Do not do that, right? You just write out your half reactions, you find their potentials listed as reductions, but you still use them as is. So however they're written in the table, it's the cathode minus the anode, go with it. That is your overall cell potential for this redox process, right? So this could generate 2.6 volts of potential, which is great. Be used to man a battery or something like that. Okay, so that is an example. Let's go ahead and do a problem to get that into your head a little bit better, right? So I have a redox process. I want you to calculate, again, the cell potential using our standard tabulated electrode potentials, reduction potentials. can't zoom in on your, no, it doesn't work like that? Okay, so go and get your answers in. We'll go over this one. Okay, so let's go ahead and talk about this one so that we have enough time to get through everything. So we've got lead reacting with chromium metal, making lead metal, chromium 3+. So who's being oxidized here? Who is the oxidation half reaction? We've got chromium, so we've got chromium solid going to chromium 3+ ions. How many electrons is it losing? 3, right? It goes from a 0 oxidation state to a +3, so it loses 3 electrons. That's important. There are multiple different oxidation states for chromium. They all have different potentials. So make sure you're noting that this is the couple that has chromium going to chromium 3+. For the reduction, who are we reducing? Lead. How many electrons is it gaining? 2. So 2 electrons going to Pb, solid. So we go to our nice little handy reduction potential table, and hopefully you can read it. Oh, I've lost mine. So for the chromium half reaction, we get a reduction potential of a minus 0.73 volts. And then for the lead half reaction, we get a potential of a minus 1.13 volts. So now, if we're going to calculate the cell potential, we're going to take the cathode half reaction, subtract the anode half reaction. So who is the cathode here? Cathode is reduction, so it's the lead reduction potential. This is 1.3 volts minus a minus 0.73 volts. Again, do not be tempted to reverse anything. So when you do that, minus a minus is a plus, and overall you end up with the point 0.60 volts. Are there any questions about that? Okay, most of you got this correct. It was just not putting it into Socrative the way I was requesting it. Okay, so that is it.